Caitlin, and I'm the educator at the Ontario Science Centre. Today I'm coming to you from my dining room and my kitchen to talk about the delicious world of solubility chemistry. Why is solubility important? It's everywhere around us, from the water that we drink to other flavored beverages that we might enjoy, transporting nutrients inside our body in the circulatory system, and helping to shape the globe around us in case of things like the Grand Canyon. Solubility surrounds us. Now, before we get started today, I do want to talk quickly about safety. Normally in chemistry labs, you're not allowed to eat or drink anything. But in this one case, because we're working in our own homes, because we're using groceries from the grocery store that we know are safe, it's okay to go ahead and sample things. The caveat to this is that you need to use your best judgment. If you're mixing different household cleaners into a bottle of pop, maybe not the best thing to try and drink. But if you're just stirring in some extra sugar, it's probably not going to hurt you. Let's get started talking about solubility. You're probably familiar with it if you enjoy flavored drinks, like maybe iced tea, lemonade, or Kool-Aid. In this case, water is going to be our solvent, the thing that's going to dissolve our solute, my iced tea crystals. If I add some of those to the water, they easily dissolve, making a dilute solution. If you like your drink sweeter, you can make it more concentrated by adding more of your solute. So what exactly happens when you dissolve sugar in water? First, let's think about our solute, the sugar. Sugar is a crystalline molecular solid, and there's intermolecular forces holding those molecules together inside your sugar crystal. So you've got to break those forces apart before the water can get in to dissolve the sugar. Now let's think about our solvent, the water. It contains an oxygen, which is very electronegative, bonded to hydrogens. Because of that, there's this dipole moment within water. And in this case, because it's an oxygen bonded to a hydrogen, we call it something special. It's called a hydrogen bond that forms in between different molecules of water. Again, we have to break those hydrogen bonds to allow the water to surround and dissolve the sugar. Once those hydrogen bonds in between the water molecules have been broken, water surrounds the sugar molecule and starts having dipole-dipole interactions between your solvent, the water, and your solute, the sugar. You can see there's a few dashed lines showing that some hydrogen bonds are formed as well.
What happens to the solubility of our solid solute, sugar, when we change the temperature? Let's make some rock candy to find out. To make rock candy, heat 1 cup of water on medium to low heat and slowly stir in 2 cups of sugar. While the sugar is dissolving, you can prepare your cup and string that the rock candy will grow in and on, as detailed in our companion document. When all of your sugar is dissolved in the hot water, carefully pour it into the glass and wait.
So what exactly is happening inside your glass? Remember, solubility is a measurement of the maximum amount of solute, in this case sugar, that will dissolve inside your solvent, in this case water, at a given temperature and pressure. For sugar at 25 degrees Celsius, that's about 200 grams in 100 milliliters of water. When the temperature is increased to about 100 degrees as you boil your water, the solubility of sugar increases to 500 grams in 100 milliliters of water. That's a huge amount. This is because the molecules have more energy, so that allows water to break more of those sugar-sugar hydrogen bonds and hydrate your solute. As your saturated solution starts to cool, that's your sugar solution that you put as much sugar as possible into as it's boiling on the stove. As it cools inside the glass, the concentration of solute exceeds the solubility. The sugar molecules are going to start to crystallize out of the solution on the string inside your glass. Over the next few days, more water is going to evaporate from the glass, resulting in more rock candy. What do you think would happen if you added something like food coloring, or even flavoring like vanilla or orange extract to your system? Would you still get rock candy? Can you think of any ways to improve our recipe? We said we were going to talk about solubility with pop, and we haven't done that yet. While most soda pop has sugar or other sweeteners dissolved inside, there's something else inside this bottle too. You probably know what it is, even if you've never thought about it analytically before. Let's do a quick experiment using this bottle of pop, a barbecue lighter, and a wooden skewer. I'm going to open this bottle of pop, then I'm going to light my skewer on fire and lower it down inside the bottle. What do you think will happen? Let's check your predictions. I'm going to light my skewer and lower this flaming splint inside the bottle. What happened to the splint? Why did it happen? What else is dissolved inside this bottle of pop?
You've probably heard the term likes dissolve likes. That's referring to polar and nonpolar molecules. Let's consider our solvent, water. If you look at the structure, you can easily see that oxygen draws electrons towards itself, making water a polar molecule. What about carbon dioxide? My friends Simon and Vicky did an activity outside to show you what happens in carbon dioxide. Here, Simon and Vicky are both pulling on the ends of the molecule just like oxygen would, trying to pull electron density towards themselves. But they're balanced out. Neither one can steal all the electrons to one side of the molecule. So, having carbon in the middle, balanced by those two oxygens, carbon dioxide is nonpolar. What does that mean for our pop?
We have water here as our liquid. Now this is just regular tap water. I'm going to add approximately 1 tablespoon of red cabbage juice, just so you can see some of the changes that are going to occur. I'm going to put my cap on and give it a good shake to make sure it's a fairly homogeneous solution. Now you can see that purplish color from the red cabbage juice, indicating that we have a neutral pH. Another piece of information that you might want is the temperature of this water. From my thermometer, you can see that we are around 25 degrees Celsius. The gas that we're going to dissolve inside our water today is carbon dioxide. It's housed inside a cylinder in the back of this home appliance. To add it to the water solution, I'm going to put the water screwed in place. I want you guys to watch right here, which is where the carbon dioxide is going to come out when I push this button. And you can see there's been some sort of chemical reaction because our water has changed color. That cabbage juice indicator has changed color, going pink, indicating what? Acid or base. What does that mean for our pop? If you pour yourself a glass at home, you can see the bubbles inside. That must mean that somehow carbon dioxide does dissolve in water. Now, when carbon dioxide dissolves in the water, some of it reacts. Look at this short animation that shows you how water reacts with carbon dioxide to create an acid. Let's get back to temperature. We had a room temperature bottle and a cold bottle. And I personally prefer to drink from the cold bottle. Why is that? You can set up and experiment yourself at home using pop at different temperatures. Here, I have 1 glass of pop that's been heated inside the bottle to 40 degrees. One is just sitting at room temperature from the counter at 21 degrees Celsius. And my third was sitting in the fridge and is now inside an ice bath. It's chilled down to 10 degrees Celsius. When you do this yourself, look at the bubbles that are forming. Is one bubbling more than the other? Are there some bigger bubbles in one than the other? What does that mean when you go to drink the pop? Test it. Try taking a sip. There's one more thing you can do just to check on this experiment. If you have or made goldenrod paper using turmeric, you can dye it red using some baking soda. Then place the turmeric paper or the goldenrod paper really close to the surface of your pop. Not actually touching, because you don't want to spoil your drink, but close enough so that some of the bubbles will actually reach up towards it. After you pull it away, you might notice that your paper has turned from red to gold. That's showing you the carbon dioxide bubbling off pop. Now, which one does this happen more to? The cold, the room temperature, or the hot? Make your predictions and test it out. So now you've tested your pop at 3 different temperatures. You probably liked the cold one the best. That's because it has the most carbonic acid inside. The hot one has a lot of acid converting to carbon dioxide and then bubbling out of the drink. That's why hot pop
like bottles left in the car on a warm summer day, go flat so quickly.
Now that you're an expert in solubility, I have a challenge for you. Can you figure out exactly how much carbon dioxide is inside a bottle of pop? There's a few materials on the table to help get your brain started. I also have a couple of questions. First, is there any way to measure the amount of gas that leaves the bottle? Second, does adding anything to your bottle, like mints or candy or even sugar, change the amount of carbon dioxide that leaves? Third, is there any form of carbon dioxide left inside the pop even after it stops fizzing? You might want to use some of your pH test paper strips or some red cabbage juice to help answer that question. You can also add some household cleaners that are often basic. Finally, does changing the flavor, the brand, regular versus diet pop, change the amount of carbon dioxide that you can get out of a bottle? Last but not least, when you're done playing with your pop, don't waste it. If you're not going to drink it, maybe see if you can find out exactly how much sugar there is in this too. Until next time, have fun.